Hi, good afternoon. I'm Thomas Gerrits, physicist at NIST in Gaithersburg. I'm leading a project on quantum network and component metrology as part of our quantum network testbed in Gaithersburg. And as part of our research team, we're working on answering this question: what do we need to build a complex quantum network? And for this, we're now setting out and have set out to set up testbed on the NIST Gaithersburg campus. We are developing metrology that is associated with the entanglement distribution in this network. And also we're working and hoping to be able to provide input to the future development of standards for heterogeneous operation of components within the network and the network itself. So we're developing the tools to enable quantum networking and enable the nascent quantum industry. And we're trying to understand the operation of quantum networks and find no-goes and potential trade-offs that we can implement. So this is an overview, a schematic of our network, quantum network testbed at the NIST Gaithersburg campus. We currently have 5 labs connected with a line of sight of about 250 meters. From one lab, we have a direct connection to a hub that then connects to a 60-kilometer fiber out to the University of Maryland and the DC QNet. And so this is a great infrastructure to do actual in-field and out-of-the-field quantum networking and experiments. So the key enablers for quantum network metrology are single photon sources, entangled single photon sources and receivers, and of course, metrology methods and the protocols. And so we have been developing these over the last couple of years or so to make them portable, to make them deployable in the quantum network and move them around nodes, move them around buildings and potentially different institutes. And here, this is a photograph of some of the sources and receivers that we've built. So by having the sources and detectors, we're now starting to perform measurements. And so we envision in the future to have these measurement nodes, these components somewhere strategically located out inside the quantum network that can then serve as the state, as generating entangled state of light, and then also characterize the state. So that can be useful for verification and quality control of these quantum links between components and different nodes. And of course, they should also be there to verify timing synchronization between the individual nodes, which is a very tough requirement. And it's on the order of 5 orders of magnitude more stringent than what is needed classically or what is being standard classically now in the classical networking. In terms of standards, we have been working over the last 1.5 years or so in a dictionary that pertains to single photon sources and detectors. These are defining metrics, and the reason for this is to promote a common language and clarity in communication so that when we talk about a metric, we know that we talk about the same metric. So this dictionary will hopefully provide clarity on data sheets between different vendors, and it can serve as a basis for standard development. And what we're actually planning on doing when this dictionary is done, to submit it to a standard development organization. And so with that, some of these definitions might become a standard. So now we have some tools and the testbed. Let's do some metrology. So these are some measurements that we have done on the testbed so far, a few selection of those. And the most important one, I think, if you connect 2 nodes, is a fiber loss characterization. And we have developed a single photon based OTDR, optical time domain reflectometer, that can measure fiber loss. And it's actually wavelength tunable. We can span the complete telecom band from the O band all the way to the U band and measure fiber loss and measure where the fiber loss occurs. So that is a very important tool and a very good tool to have. On the long fiber link out to the University of Maryland, that's a 60-kilometer link, we have measured the polarization stability. And we have found diurnal variations, and the variations, the speed of variations will change compared to night and day. it really helps. These measurements and these kind of measurements really help to determine the bandwidth on which fiber polarization has to be stabilized in these fibers. We have also looked into quantum node synchronization using some high accuracy protocols. We're able to synchronize on the NIST campus nodes down to 5 picosecond peak-to-peak precision, and on a metropolitan scale down to 200 picoseconds. So with this, these are really useful tools, measurement tools, to characterize your link, to characterize the synchronization. And now we want to, of course, distribute entanglement and perform swapping experiments, teleportation eventually. And so these tools can be used to first characterize the link, but then we also need the sources. And this is an example of a source that was distributed over 140 kilometers with entanglement, polarization entanglement. And it's very promising to be able to use that in the future for our metropolitan links. And so last but not least, we also looked into quantum classical coexistence that comes down to the noise problem that Mark alluded to earlier. We're able to characterize the loss in fidelity or reduction of fidelity for this polarization in stable state when we also coexist the classical signal in the same fiber as the quantum signal. And so with this, I would like to conclude, put up my contact information here, and please reach out to me if you have any questions. And thank you for your attention.